All right. I got a little surprise for you guys in this video. Oh, I said all right again. Oh, well. So let's introduce the fundamental theorem of calculus, all right? Otherwise known as the evaluation theorem. The FTC part 2, sometimes known as the evaluation theorem. Says that if f is continuous over a to b, very shocking start. Everything has been this assumption. And f is any antiderivative. We introduced antiderivatives 2 videos ago. The backwards of derivative. S is any antiderivative of little f. Then the integral from a to b of this function. This is the shortcut. This is the moment you've all been waiting for. The formula to prevent us from taking Riemann sums. This fundamental theorem of calculus, this amazing theory that you will love and love and love to the end of your calculus days, is coming. Instead of doing all those Riemann sums, we got this nice, beautiful formula. And all it is plugging in 2 numbers and taking the difference. That's it. You've set up these Riemann sums. You've calculated the areas of 1 billion rectangles. Well, all you need to do is plug things in and subtract. Of course, the difficulty and what we'll be talking about for the next 2 chapters of this class is sometimes finding this guy is a little squirrely. But that's what we're going to be mostly doing in this video. Here's the fundamental theorem of calculus, and then we're going to talk about how to find that antiderivative. And that's the little surprise here, because this textbook wanted you to do this in volume 1. But usually, it's hit or miss, but a lot of Calc 1 classes that I'm aware of don't cover antiderivatives in number 1. So we're going to jump and do an entire section from Calc 1 textbook in this video. So this video is just a whole section. But don't worry, we'll get a lot of practice with antiderivatives. So before we really talk some more about how to find an antiderivative, I want to connect part 1 and part 2 just a little bit. Look at if we have something like this. This is maybe optional to write down. But look at what the fundamental theorem of calculus part 2 says about, I'm not going to include this bracket. It says, fundamental theorem of calculus part 2 says that this is capital F of the upper limit minus capital F of the lower limit. And if we take the derivative of both sides, what happens? Well, if we take the derivative of the left-hand side, we get the fundamental theorem of calculus part 1, giving us f of x. And if we take the derivative of the right-hand side, we get f prime of x. This is just a number. A function evaluated at a number is just a number. Well, that's the definition of an antiderivative. So this is, of course, true. So it's just one way to see one of the relationships. There's a lot of relationships. But one of the relationships for part 2, which, again, we're not going to prove part 2. It's in the book. It's not bad, but I just don't know if it's so important to fit it into this video when we've got a whole section to cover. So we're going to start by talking about indefinite integrals, just because it makes the notation a lot better. We've talked a lot about definite integrals, the integral from a to b. Indefinite means not definite, and so we're just going to lose the limits of integration, basically. So, definition. If f, capital F, is an antiderivative of little f, it being an antiderivative means the derivative of capital F is little f. Okay, then the indefinite integral which is written, and that's our definition, as the integral of little f of x dx. So just like a definite integral, just with no limits of integration. So think about it as like a general integral. This is our antiderivative. Another way of writing that. If capital F is any antiderivative, then the integral, the indefinite integral, is just that antiderivative plus any constant for any capital C that's a real number. There's infinitely many antiderivatives, and we write indefinite integrals this way. Because if I take the derivative of this and we look at the slope, no matter what C is, if I take the derivative of this, we get F. So no matter what C is, the big circle will be an antiderivative. All right, another way of phrasing it is, right, it doesn't matter if we have constants attached to this by addition, because when we take the derivative of it, they're going to go away. So they'll all have the same slope. So when we talk about indefinite integrals, this is what we do. And this notation is just a lot nicer. Like if you remember way back when I was trying to give an example over here, down here, when we introduced antiderivatives, I just wrote it out in words because there wasn't a great way to write it. Well, now we have a great way of writing antiderivatives. We can think of antiderivatives more or less synonymous with indefinite integrals. Okay, there's some tiny subtleties, but more or less the exact same thing. So let's get into it. Let's find some. So the good news is that for most functions, for most simpler functions, most functions that aren't super complicated, you've already done this. Everything in Calc 2, everything in Calc 1 applies to Calc 2 in some way or another, right? I said earlier that, the derivative of x squared is 2x. So we know now that the antiderivative, or the indefinite integral of 2x, is x squared. Any formula we have for derivatives is also a formula for integrals. So it's very important that you have good Calc 1 notes, because every single derivative formula is now going to have an integral formula. And we're not going to do it over 8 sections. We're going to do it right now. So if you'd like, you can just use all your Calc 1 notes in this fashion with every differentiation formula that we have. Okay. Or if you really like having things organized and in the same place and in the right notation, you can go, and I will link this for you, but you can go to volume 1 in OpenStax, section 4.10, and this has everything that we've done. So we have all the differentiation formulas on the left, and just like I wrote down in blue, every differentiation formula is also an integration formula. So if the derivative of an exponential function is itself, the backwards of that is that the antiderivative of an exponential function is itself plus any constant. Because remember, there's infinitely many antiderivatives here. And likewise, we have the power rule. Instead of bringing down a power and subtracting it, we go backwards. We add a power, and then we divide by that new power. So this is probably going to be the most important rule, and I will manually write this down. This one is what we'll write down together, but everything else, you can write it down if you'd like. We'll be using it. But the most important are power rule, which I will write down, exponentials, and our basic trig, these 6 ones right here. Everything else we have, remember the derivative of inverse tangent was 1 over 1 plus x squared. This one will pop up too, but we got a lot of formulas. I'm not going to write them all down. You have all of these in one form, just a new form over here. So power rule. That's the one we'll cover explicitly today, but we'll use all of them. The antiderivative of x to some n, where n is, well, I'll talk about what n is soon. That's equal to if we add an exponent and then divide. And notice not only are we doing the inverse, division instead of multiplication, and adding instead of subtracting, we're also doing it in the opposite order, right? Normally we bring it down and then subtract. Well, now we add and then divide. So it's being done in the inverses and the inverse order. And if you remember some stuff about inverse functions, that's consistent with how we think of inverse functions. And then again, always add the plus c. I will give points for plus c. Plus c is points because it's important to remember there are infinitely many antiderivatives here, and we can choose any one we want. And in fact, for a lot of application problems, we'll take the antiderivative and then we'll have to find which c makes sense for this application because there's infinitely many. But we'll cover that more in the future. Okay, so this is the one that I want to mention here, and n is almost anything. N is any real number except -1. And very briefly, why is that? If n is -1, we have this. And if you tried to use the power rule, if n were -1, you'd add a power to get n to the x to the 0, and you divide by a power, divide by 0. Don't want that. But remember what the derivative of natural log is. The derivative of natural log is 1 over x. So that's what we write over here. And in fact, we can make things even more general by adding absolute values. Because it's actually true for positive and negative x, even though natural log is only defined for positive x. Now we get a lot more information if we add the absolute value. But anyway, let's get some practice with these. Going backwards. Got 5-ish examples for you. Find the antiderivative f of x for the following functions. So use the power rule backwards. Again, we know that the antiderivative of x to an exponent with respect to x. I'm just checking to make sure I wrote my dx's because I sometimes forget that. Is add a power and divide by that new power. That's all we do. Oops. So f of x, which is also known as the antiderivative of f of x, which is also known as the integral or indefinite integral of f of x, is going to be what happens when we add a power and divide by that power. You can divide by 4, multiply by a quarter. They're the same. And there we go. And you can always check your answer because the derivative of an antiderivative should cancel each other out. Derivative of an antiderivative is the original function. So if I take the derivative of this, power, bring down the 4, 4 over 4 cancels, subtract an exponent. Great. That's an easy way to check your answer for integrals. Derivatives, there weren't easy ways to check your answers unless you use the limit definition or something. Antiderivatives are much easier to check your answer for. So let's get into the habit as a class, and I'll try to do it myself, of checking our work. X squared plus e to the x. So just like with derivatives, where we can just add derivatives together, integrals are the same way. In fact, we had that property for definite integrals, and those properties for definite integrals hold for indefinite integrals as well. The antiderivative, well, here we'll use the power rule. We'll add a power and divide by that new exponent. What about e to the x? Well, we know that the derivative of e to the x is e to the x, so the antiderivative of e to the x is also e to the x plus a constant. So that's our first derivative. Our first antiderivative. And this is our second antiderivative. But it could be a different constant. They don't have to be the same constant. We can call this first constant C1 and the second constant C2. It's any constant. But any constant plus any constant is still just a constant. So this is a little redundant. So basically, we'll always just jump to combining those constants. Okay, even though we're taking this, finding this antiderivative and finding this antiderivative, they could be different constants, but since it can be any constant, any real number plus any real number is still just any real number. And we could check our answers by taking the derivative. We use the power rule and the rule about exponentials. Yep, we get the original function again. Let's run through some more of these. Part C. What if we want to find the antiderivative of 2 times the sine of x? So again, our properties of definite integrals, remember that we know for integrals, if we're trying to take the integral of a constant times a function, that's just the constant times the integral. So all we need is the antiderivative of sine. So you might think you can consult your table that I didn't write down, the table in the book. You could consult this table to get the formula, or you could try to come up with it yourself. But be careful, because this formula is not helpful here. The derivative of sine is cosine, but that doesn't tell us the antiderivative of sine. This gives us the antiderivative for cosine. Right? This tells us the antiderivative of cosine is sine. So the other one we want to use is this. The derivative of cosine is negative sine. Let's multiply both sides by a negative to make things a little nicer. So the antiderivative of sine is negative cosine. Or again, you can use this table. Antiderivative of sine is negative cosine plus c. We have 2 times negative cosine. And we can put the negative out in front. Can check our answers by taking the derivative. Negative 2 stays in front. Derivative of cosine is negative sine. Negative times a negative is positive, and we have sine of x. The derivative of a constant is 0. So yeah, we get the same thing. F of x equals... I made up an example, but I actually made up an example that's secretly really hard. That's funny. I made up the example of secant x. But that's no good. Let's do the example of secant squared of x. Later on in this class, I'll tell you how to take the antiderivative of secant x. It involves like logarithms with trig. Let's skip that. So again, we need to find the derivative. Here's another way of doing these problems. The derivative of what is equal to secant squared of x? This is our antiderivative. So what do we take the derivative of that gives secant? Tangent. In fact, that's probably the best way of approaching these problems. I should have phrased it that way in the previous ones. Yeah, do that again. So this is just going to be tangent of x plus c, and we can check our answer by taking the derivative. So again, back here, it was the derivative of what equals sine of x, or 2 sine of x, depending on how you want to approach it. And the answer was negative cosine. Here, in this top one, right, the derivative of what equals x cubed. And the answer was 1/4 x to the 4th plus c. All right, last problem of the video. F of x equals x e to the x. So the derivative of what is equal to x e to the x? And this is where things get fishy. For derivatives, we have the product rule. For integrals, there's no exact product rule, but there's something we'll use instead that we just honestly don't know yet. It's called integration by parts, and we haven't learned it yet. So we don't have tools to do this problem yet. So why did I introduce it? Because I want you to remember the product rule, and remember kind of a good rule of thumb for Calc 2 is that integrals are harder than derivatives. We can, I believe that we can take the derivative of any closed function, a function with a closed formula. Any function that we can write down the formula for, we can find a formula for the derivative. 99% sure about that. I'm sure there's a proof online, but I just didn't think about it before making this video. Integrals, that's not the case. There are some functions that we just can't take the antiderivative of. We can get computers to approximate it for us, but there's no normal function for these derivatives. The simplest of which is, so hold on, let's say, can't do this yet. We need integration by parts. And you can try, if you want. I would love to see if you can guess what the answer is. It's pretty hard to guess, but it's definitely possible. Basically, we need something that undoes the product rule, kind of. And that's a little squirrely. We'll get into that in chapter 2 or 3, I don't remember, in this class. Okay. But yeah, one example is this guy over here. The derivative of this is no problem. All it is itself times 2x. It's just the chain rule. But the derivative of this, or the antiderivative of this, is much harder. In fact, I believe this is the imaginary error function. It's called like ERFE, I think. And we just use computers to approximate it, basically. And we know some things about it, but not very many things. And there's no good formula for this. So this thing, even though it looks pretty easy, is actually pretty messy. Yeah, I'm pretty sure it's the imaginary error function. Or it's related to it, yeah. For the definite integral. The definite integral uses the imaginary error function, which is, you can Google it. You can Google it. It's cool. It's cool. But yeah, that's a summary. Antiderivatives are usually much harder to get than derivatives, but we can check our answers, which is great. Okay, that's this video. 2 more videos, really just one, and then some extra practice problems. Yeah, we'll do some examples with the fundamental theorem of calculus. Usually the hardest part is just this stuff, finding the antiderivative. Because remember, fundamental theorem of calculus is just plugging in 2 numbers and taking the difference once you have the antiderivative. So good luck. Let me know if you have questions.